Hello student, it is lecture for BSc-TY student, Linear Algebra paper 13th, lecture is 21st and semester is 5th semester. So in previous lectures, we discussed some lemma and some theorem about the linear independent and linearly dependent vectors. So today we have to discuss one theorem. I write here statement of that theorem. So if nu1, nu2 to nu_n are in V, then either they are linearly independent, or some VK is a linear combination of the preceding ones. That is K minus 1. So this is very interesting theorem. This asked frequently in examination. So what is this? If nu1, nu2 to nu_n are the vectors, n vectors in vector space V, then either they are linearly independent. So there are only two possibilities. Which possibilities are there? Then either they are linearly independent or some Vk is a linear combination of the preceding ones. So some Vk is a linear combination of preceding ones means they are linearly dependent. So it is very trivial statement. Whatever the numbers of vectors in vector space V, there are only two possibilities. Either they are linearly independent or they are linearly dependent. So if they are linearly independent, there is no chance in their linear combination. All constants must be 0. And if they are the linearly independent, then some of them must not be 0. That means one vector can be represented as preceding one's vectors, linear combination of preceding one's vectors. Okay, now we discuss its proof. So if these vectors Vn are linearly independent, so there is of course nothing to prove. Isn't it? It is trivial. If nu1, nu2 to nu_n are linearly independent, so there is of course nothing to prove. If linearly independent, then by definition of linearly dependent, all their constant must be 0 and nothing to prove. Suppose then that alpha 1 nu 1, alpha 2 nu 2 and alpha n nu n is equal to 0 where not all the alphas are 0. If linearly dependent, then all alpha 1, alpha 2, alpha n 0. But suppose this is a linear combination is equal to 0 where not all alphas are 0, not all alphas are 0, so some are not equal to 0. Let k be the largest integer. K be the largest integer for which alpha cannot equal to 0. Since alpha is equal to 0 for I greater than k. Suppose up to the alpha k is not equal to 0, then alpha is equal to 0, then I must be greater than k because it is the largest integer k where the alpha k is not equal to 0. So this linear combination alpha 1 nu 1 plus alpha 2 nu 2 to alpha k nu k is equal to 0 since alpha k not equal to 0. So in this linear combination all alphas are not equal to 0. So this implies that I can write this Vk. Firstly I write this Vk alpha k is equal to transpose this all terms to the right side and we get minus alpha 1 nu 1 minus alpha 2 nu 2 and so on. Without writing this positive sign we write negative, so it will be convenient. Then minus alpha k minus 1 nu k minus 1, right? So this nu k is equal to alpha k inverse into minus alpha 1 nu 1, minus alpha 2 nu 2 and minus alpha k minus 1 nu k minus 1. So multiplying this alpha k inverse, so we get alpha k inverse and alpha 1 in one bracket and there is nu plus minus alpha k inverse alpha 2 into nu 2 and so on. Last is alpha k inverse minus alpha k minus 1 nu k minus 1. So all these are constant, and there is a nu 1 nu 2 to nu k minus 1. K minus 1 means this nu k and after that nu k minus 1. So all these nu k minus 1 vector, nu 1, nu 2 to nu k minus 1 vector are a linear combination and it represents nu k. And it represents nu k. Thus this nu k is a linear combination of its predecessor, is a linear combination of its predecessors. So student, this theorem is over. Thank you very much.